Hi, everyone. My name is Duncan Watts, and I'll be giving a lecture today on the sampling of components amplitudes in Commander 3. This lecture is best viewed in conjunction with Tryggve Spalheim's lecture, which is on the spectral index sampling in Commander 3. The two are deeply related, but thought we'd give you a little break between the two. Okay. So just a big overview of the picture. The data model in Commander basically says, here is your amplitude of different foreground components. How do we take them as closely to data space as possible? And so essentially the order of operations is you evaluate the spectral energy distribution of your component at the frequency you want to observe it, smooth all of your maps to a common resolution, add all those components together, and then you compare that data model to what you actually observe. And so this is essentially the process then. So on the left-hand side, we have the amplitudes for all the different components. And on the right-hand side, we have the Planck LFI bands. And these are the final process maps. Now, there's another version of this called component mapmaking, which is a little bit beyond the scope of this, but I'll talk, and it's not actually implemented in Commander, but generally what we do is do the mapmaking, compare the maps to the amplitudes given the components evaluated at a certain frequency. So in very raw forms, the data model in matrices is given by essentially a mixing matrix applied to a series of amplitudes, smooth to the resolution you observe at. A pointing matrix is applied so that you have a map taking from pixel space to time ordered data space, and then the gain is applied. And so this is essentially the thing that will allow you to compare your component amplitudes to your data, given that you know what your gain is, what your pointing is, what the beam is, and what the mixing matrix is. And of course, and then, of course, you use all these things to sample for the amplitudes. And if we assume that this is a Gaussian model, that is, that you have Gaussian white noise, this is actually it is simply a Gaussian sampling routine. And I mentioned the mixing matrix a few times, and it's come up a few times in the course, but it's always worth reviewing. I generally think of the mixing matrix as the recipe for turning one SED into what a given detector observes. So in a very in a perfect situation where we have delta function bandpasses, that is, your experiment observes, say, exactly 31.25, et cetera, gigahertz, you can evaluate your SED, that's what a FI is here, of your frequency of one component, say synchrotron, at exactly that frequency, given spectral energy distribution parameters, in this case, beta, the spectral index. And this will allow you, if you put it in this form, it essentially becomes a linear operation from each frequency, from each component to each frequency. So you end up getting an n component by n frequency map. And so in this case, you would have one component that's essentially just the CMB that would be constant. You have another row that is synchrotron, another for dust, all the way for each n components. And then for each of the frequencies, you have different evaluations. So new one, new two, new band, et cetera. And so this allows you to essentially, like, if you have the spectral energy distribution parameters, then you essentially you have the answer in what sense. And so Tryggve's lecture talks about the hard part. How do you actually figure out what the beta S and beta D are? But if you know exactly what they are, the problem becomes quite simple. Now, of course, with the mixing matrix, you need to take into account the spectral energy distributions of the interaction with the bandpass. So as a toy example, again, looking sort of like synchrotron, we can imagine, if we know that the beta is minus 3.1, you can write down, like, this is what the response is going to be. And if you have a delta function bandpass, you essentially can just pick out the frequency that you observe at. But real band passes are a little bit more complex. So for example, this is a WMAP Q band band pass. And when you evaluate the frequency here, you could say, what is the effective frequency? Or you could essentially compute the integral over the bandpass tau multiplied with the synchrotron, and then you could say this is the expected frequency response of the Q-band instrument. And so this is another thing that is taken into account, and this integral is actually one of the main reasons why it's useful to have the mixing matrix, because it's not exactly a trivial operation to compute this integral. And if the spectral energy distribution doesn't change, this is something that you could just sort of keep in memory and sort of compute sort of once per Gibbs sample instead of computing this integral for every Gibbs sample. So this is a large time-saving thing, and I think part of the motivation for why we have a mixing matrix at all. So given this is a little bit closer to what we have actually implemented in Commander. Again, we have the spectral energy distribution, but this time it's integrated over a bandpass. And it reduces to the previous case if tau j is a delta function in frequency. And then, of course, there's a unit conversion. Sometimes you have experiments that measure in K, C, and B, sometimes K Rayleigh genes, Megajansky's per steradian. So all that goes into the U factor for a unit conversion. But yeah, so I just wanted to make sure this is all very clear. And also, if you have fixed spectral index parameters, this is something that you can essentially compute exactly once. And this is kind of why spectral index sampling is a bit more complicated, because you need to recompute the mixing matrix. But if for some reason you believe you know exactly what the spectral index parameters are, you can just compute the mixing matrix exactly once. And in fact, in Commander, there's an option to sample only for the amplitudes. And it's a lot faster precisely because we're not computing this integral every time we do a Gibbs sample. Okay, so I sort of alluded to this before, but essentially this is what the data for WMAP looks like. These the black points are what WMAP observes, and this red line is the full pointing, gain, beam smoothing mixing matrix applied to the amplitudes. And so in principle, one could just solve for the amplitudes directly from the time streams. And this is, as we've seen before, there's this data is given by TA plus n, where it's a Gaussian, so as a maximum likelihood solution given by this. And in principle, we are also interested in using informative priors on the amplitudes. And what that ends up doing essentially is, if you turn through the algebra, you can use the prior mean here, which essentially uses the prior covariance, and then there's the prior covariance on the left side as well. And so obviously you can see if S inverse becomes uninformative, or the noise covariance matrix is sufficiently small, so the inverse noise covariance is very high, you start to become data dominated again. So you see it reduces to the maximum likelihood solution. Now, of course, the pointing operation is basically projecting the map into data space is quite computationally difficult, and this is something that we do not have currently implemented in Commander. However, it is equally valid to just do map making first. And this is a case where instead of using the raw time ordered data, D equals TA plus N, instead we have the data being the maps, where we apply the mixing matrix of the amplitudes and smooth them, and then we can compare that to the maps that we observe. And so this is one of the brilliant things that was implemented in Commander 2, where we are able to smooth the amplitude maps and compare maps at different resolutions, as long as we're comparing the chi-squared, the goodness of fit in the map space. We can compare the data, we can compare the model evaluated in data space on the same footing. And so in the same case, basically, this template matrix is exactly the same as before, except now we have this sum over all the frequencies. As compared to the TOD map making or the component map making, this is much simpler to implement because we can just create the maps for each band individually and then do the map making later. This smoothing of multi-resolution data to a single space that allows us to take, say, for example, the Haslam 408 megahertz map and Planck 333 gigahertz and use both of them as templates. This requires some smart preconditioners. This is a system that's somewhat difficult to solve. Partially this motivated our change to work completely in spherical harmonic space rather than pixel space, which if you're interested in that, that's worth another lecture on, but basically this is half of what we're doing here. So yeah. And I do want to point out as well that this kind of starts to reduce to the usual template-based map making that we're used to. So you may have heard of the internal linear combination method, where you take linear combinations of different maps to solve for different components. So in a sense, if you work through the algebra here, this A for each component is a linear combination with the correct coefficients. And with methods with blind component methods, you don't know what the coefficients actually need to be. But because we're working in a Gibbs sampling framework, we know exactly what the spectral index parameters are, so we can compute exactly what the components are, given the SED, what the amplitudes are at the end. So this is this might be a little bit more familiar of a framework for some people who work with, for example, just linear combination methods. I'm saying that again here, of course. You could write it as A equals the sum over the weights. In this case, it would just sort of be scalar. But of course, like adding different components ahead of time with using the different smoothing and different resolutions, this is a little bit more computationally correct than just doing linear combinations of maps with a single frequency. Using maps with a single value across the whole sky. So that's a little bit of why this is a bit complicated here. Although mathematically it's quite easy to write down the inverse of this matrix, and so a lot of the work is going into actually solving this equation. Once writing it down, this part of the equation, writing down the term in the parentheses, and then solving for A. Yeah. So as a reminder, this is the Commander3 Gibbs sampler in all its glory. The amplitude sampling is just one small step in this entire framework. And again, we're taking everything constant, so it actually simplifies things quite a bit. Now, if you've seen Hovard's lectures on sampling, we know that given a prior X, if we want to actually draw samples rather than just solve for the maximum likelihood, this requires adding fluctuation terms, essentially one fluctuation term for each term of the covariance matrix. So this T and inverse T, see the square root of that multiplied by the Gaussian, standard normal Gaussian, and then the prior term, S to the negative 1/2, corresponds to this term, S inverse X. So essentially, all we have to do is evaluate to draw a sample of A given the data. We construct the maps, and then we have our model where we apply them to the amplitudes, and we have the maximum likelihood term here, the prior term here, a fluctuation term from the data, and a fluctuation term from the prior. And this is a bit complex, so I'm going to sort of try and break it down a little bit. So for one thing, if you remove the prior and the mean term, if you remove the prior term, you end up getting just sort of a simple fluctuation. And then if you remove the fluctuation term again, you start to get something that looks a little bit simpler. And then finally, if you invert this matrix, it turns into something, again, that looks like a simple linear combination of matrices. But of course, we can't take that inverse, and we want to take random samples, and we want to have priors. So in Commander, what we end up doing is solving this equation iteratively. Again, making a guess for A, and then essentially refining that guess through an iterative procedure such as conjugate gradients. All right, I know you've all seen this data model before, but essentially all we are fitting for here at this stage in the Gibbs chain are these amplitude parameters. And as you can see, this is independent of the SED parameters, so it allows us to do some kind of nice things. We don't have to worry about the spectral indexing stuff because, again, we're taking it to be completely fixed. Now, even if we sort of know what all of the spectral parameters are, it still matters how many data points you have. So here I've sort of done a degenerate system. So, imagine you have this is 4 SEDs, something that looks like synchrotron, something that looks like free, something that looks like dust, and something that looks like CMB. And say you have measured at 3 frequencies. Essentially, this is a completely degenerate system. You could imagine changing the amplitudes of any one of these to make any data point mesh. What you really want to do is add more data points so that there's like less wiggle room for each of these, but the systems are still somewhat degenerate. You could imagine the synchrotron-like and the free-like parameters. If you adjust their amplitudes simultaneously, there are ways that you can make the data be slightly better fits or comparable fits just by doing this. And essentially, the way that we can say this mathematically is that the system can be written as AX equals B. And if you think of A as all of the mixing, all of the taking components to map space, that matrix A has a high condition number, which basically means that the maximum eigenvalue is much larger than the minimum eigenvalue. And essentially, if you add more data to this system, the condition number becomes a little bit closer to 1. You want to have the eigenvalue spectrum as close to 1 as possible to solve the matrix easily. So basically, if you just solve for all the amplitudes at the same time, you would kind of be in trouble. Now, and again, you've probably seen this all before, but this is, again, where Gibbs sampling can help. So before, we've been talking about Gibbs sampling by holding the spectral parameters fixed while solving for the amplitudes. But what I'm going to propose here is that we hold most amplitudes fixed and solve for another amplitude at the same time. And so this essentially makes it a much smaller system. So rather than, say, solving for 8 component amplitudes, you could solve for 3 at a time while holding the rest fixed. So for example, basically the iterative components before, you can solve for the synchrotron amplitude while keeping the rest of them fixed, solve for dust while keeping the rest fixed, and then solve for CMP while keeping the rest fixed. And this is something that you can implement yourself in a Gibbs sampler, and you can see this behavior. So one example of how this manifests in the Commander3 pipeline is, say, with the gain parameters versus the bandpass shift parameters. You can see that the gain parameters have fluctuations that are sort of around the mean, and it looks like you can see like a relatively short correlation length. The points at the left-hand side don't know that much about the points sort of in the middle. Whereas if you look at the point, this orange line, for example, at a point here, it's quite correlated. And so it's quite dependent on points that are very far away. And this is something that you can see with sampling the synchrotron, dust, and CMB independently of each other. So I just want to take a step back and point out what we're doing. So before, we were talking about solving for all the amplitudes at once, and we have a difficult problem in linear algebra to solve. That is, we have a matrix with a high condition number. With the Gibbs sampling, we can say, well, what if we have instead a matrix with one component? We're essentially solving for one operator at a time. And that's very algebraically easy. That's got a condition number of 1, and it's very fast to solve. But the parameters themselves are very correlated, and we get long correlation lengths. Perhaps there's a middle ground. And this is where we use groups of amplitudes rather than amplitudes all at once. So in a Commander parameter file, we define these things called conjugate gradient groups, or CG_groups, where we essentially have small subsets of the parameters that are themselves correlated. So for example, CMB, dust, and free are all relatively correlated parameters. This is an algebraically simple system to solve, but the parameters themselves, if you sample them individually, would be quite correlated in the Gibbs chain. And so by sampling all 3 of these jointly, you are sort of going around the issue of them being correlated in the Gibbs chain. You're able to essentially make a draw from this much wider distribution and explore the parameter space very efficiently in a single draw. And then, and so in this example, the CG groups we have are CMB, dust, and free, then synchrotron and dust, and then sampling the monopole amplitudes, which is another, that's a fairly difficult parameter to sample over. And so it makes sense that it requires its own sampling group. And you might notice as well that dust is sampled in both of these. And this is completely legal in Gibbs sampling. There's nothing saying that you have to keep the same, you can only sample it once during the Gibbs chain. All that's required is that you use the results from the previous step, so you don't want to break the chain. So each parameter is dependent on the previous draw. And so sometimes this makes sense. You want to draw these correlated parameters together in the algebraic system rather than the Gibbs sampling system. And so this is just one of the ways that, one of the many tricks that we've employed to sample this somewhat ill-conditioned system. Because as you can see, you know, if you go through a Gibbs sampler yourself, you will see that like some amplitudes are truly degenerate with each other. There is a physical system where you could look at it mathematically and say, yes, adding CMB is essentially can be balanced with adding synchrotron. These two things are sort of equivalent with each other, and there's a true negative degeneracy. And the whole point of Commander is to efficiently probe this degeneracy in a way that doesn't take a very long time for each of the, either in Gibbs samples or in matrix manipulations. So this is currently the system that we have right now. So we use for intensity, we have Haslam 408 gigahertz, the 0.408 gigahertz, and of course, you know, WMAP, Ka, Q and V, Planck LFI, and Planck 857. This is all that's gone into the Beyond Planck runs currently. But the future is going to look a little bit more like this. Of course, you know, the Planck data exist currently, but they haven't been incorporated fully into, well, of course, there's NPipe, but in the current Commander end-to-end Bayesian analysis, the Planck HFI hasn't been included. Derby hasn't been included explicitly. SPass and CBAS and ChiPass, these are all data sets that are going to be very important for probing the degeneracy between, say, synchrotron and free, as well as Haslam. And basically, the more anchors you add, the less degenerate the system becomes. And so this will make things a little bit easier to solve, even in sort of the fully, maybe perhaps making it more possible to do a joint sample of all the amplitudes at once and having an algebraically more tractable system. But in the meantime, the conjugate gradient groups is a way that we can get around that. And so this is, of course, you know, the goal of the Cosmoglobe project, which shameless plug. These are all things that we're trying to do. You know, incorporating Derby data and all the WMAP time order data, ChiPass, et cetera, into the full end-to-end framework. And so once we do that, it'll be easier and easier to constrain the amplitudes of this highly degenerate system in a physical way. All right, and with that, I will encourage you, if you haven't watched Trygva's lecture yet, please do that now, because it goes through a lot of some of the things that we've mentioned here in a little bit more detail. And of course, it's got the benefit that Trygve has actually done a lot of the code development in Commander for some of these things, whereas I have recently started to understand it. So in that case, happy to, please let me know if you have any questions. Thank you.